Okay, so AI models and the data they need to learn, they're getting absolutely huge. I mean, gigantic. And because of that, we've kind of hit a wall. The old way of doing things, training on just one computer, it just doesn't work anymore. So the big question is, how on earth do you train a truly massive AI? Well, let's dive right into the secrets of large-scale machine learning.
So, let's talk about a monster of a model, something like GPT-2. You might be wondering, how do you train that on a single computer? And well, the short answer? You don't. You just can't. A model that big literally will not fit on a single graphics card. It's a hard physical limit that has forced engineers to get really, really creative.
I mean, just look at that number. Over 1.5 billion parameters. You can think of every single one of those as a tiny little knob that the AI has to get tuned just right. And trying to cram all those knobs into one tiny space and tune them all at once, yeah, it's pretty much impossible. So what's the solution?
Well, this brings us to what folks in the industry call the AI scaling problem. And it's not just about, big numbers on a screen. This is a real fundamental barrier in computing. When you get right down to it, the problem is actually pretty simple to understand. Everything is just too dang big. The models themselves and the absolute mountains of data you need to feed them, they've just outgrown what any single machine can handle.
Yeah, if you've ever tinkered with this stuff, you've probably seen that dreaded out-of-memory error pop up. It's basically your computer screaming, nope, no way. You're trying to fit a skyscraper in a shoebox. It's the system telling you that your ambition is just bigger than its memory. But to get around this, engineers came up with a couple of really clever solutions.
All right, solution number one. This is what you do when the model is the giant you're trying to wrestle with. The technique is called model parallelism. So the key idea here is pretty brilliant. Instead of trying to force this whole enormous model onto one poor, overworked GPU, you just slice it up. You put different pieces of the model on different GPUs, and then you get them all to work together, like an orchestra. And this skyscraper analogy, it makes it all make sense. So picture your giant AI model as a skyscraper, and each GPU you have is just a small plot of land. Right away, you know you can't build the whole skyscraper on one tiny plot. It just won't fit. So what do? With model parallelism, you build the first few floors on one plot of land, the next few floors on another, and so on. You're literally distributing the layers of your model across multiple GPUs. Okay, but what if your model isn't the problem? What if it actually fits just fine on one GPU, but your data set is the massive, unwieldy beast? Well, that's where our second solution comes into play, splitting the data. This one's called data parallelism. And here's the key difference. With this method, every single GPU gets a full, complete copy of the model. So instead of slicing up the model, you slice up the data. You chop it into smaller chunks and you feed a different chunk to each machine to work on. Oh, and I love this kitchen analogy for it. It's perfect. So imagine each one of your GPUs is its own little kitchen, right? And in every kitchen, there's a blender. That's your AI model. Now, you take this massive pile of ingredients, that's your data, and you split it up among all the kitchens. They all start blending their little portions at the exact same time. Then, at the very end, you pour all the little smoothies together to make one giant, perfect smoothie. And that is your final trained model. So there you have it. Two really powerful techniques, but let's put them side by side so we can get a super clear picture of when you'd use one versus the other. Honestly, it boils down to something this simple. You use model parallelism when your model is the giant beast that won't fit, and use data parallelism when your data set is the problem, but your model is actually a manageable size. It's all about figuring out where your bottleneck is. This chart is a great way to see it all at a glance. So what gets split? In one, it's the model. In the other, it's the data. Simple enough. But now check out communication. This one's important. It's way higher for model parallelism. Why? Because all those different floors of the skyscraper have to be constantly talking to each other. With data parallelism, though, the kitchens pretty much work on their own and only have to chat at the end to mix everything together. Okay, so we've got two awesome tools in our toolkit. But here's the thing about large-scale AI. You don't always have to choose just one. In fact, the real magic starts to happen when you ask a simple question. Hey, why don't we just use both? Exactly. I mean, think about it. You wouldn't try to cook a huge Thanksgiving dinner with only an oven or only a stovetop, right? No way. To make a real feast, you've got to use all the tools in the kitchen, and you have to use them in the right combination.
And this quote just hits the nail on the head. The most sophisticated, cutting-edge training setups, they don't pick one or the other. They create the perfect recipe that uses a mix of both to get the absolute best results.
Which brings us to, I think, my favorite analogy of the whole explainer, the range cooker. It's just a perfect way to think about this hybrid approach. So stop thinking of your whole computing setup as just one tool. Instead, picture it as this big professional kitchen appliance with lots of different functions.
Here's how it all connects. The oven, that's your model parallelism. You use it for that one huge thing that won't fit anywhere else, like the giant turkey, which is your AI model. You might even have to cut it up to fit it into different compartments. At the same time, you have the stovetop. That's your data parallelism. You're using all the different burners at once to cook up a bunch of smaller side dishes, and those are your batches of data.
And this right here is the main takeaway. To create that amazing complete feast, you use the oven and the stovetop at the same time. And that's exactly what AI engineers are doing. They'll take a massive model and split it up across a bunch of GPUs. That's model parallelism. And then, on top of that, they'll feed chunks of data to that entire setup. That's data parallelism. It really is the best of both worlds.
So that leaves us with a final pretty big question. Right now, we have this brilliant recipe for training these massive AIs, but these models are doubling in size every few months. I mean, the growth is just exponential. So you have to wonder, how long can this recipe actually keep up? What happens when even this awesome hybrid approach isn't enough anymore? And that right there is one of the most exciting and maybe a little scary challenges for the entire future of AI.